All right, last class, we were working on moles. We introduced the concept of moles. Does anyone remember the magic number that's associated with moles? Yeah, 6.022 times 10 to the 23rd power, which is Avogadro's number, which we see here on the slide, also written in as n sub a. So this magic number, this Avogadro's number, this converts between whatever our smallest little tiny particle is and 1 mole. It can be for any unit. It could even be for donuts. We could have a mole of donuts, not in this life, but maybe in the next, because we just don't have time to bake that many donuts, frankly. The other magic numbers we're using are the quantity molar mass. Molar mass is what we're always going to be using to convert between grams and moles, and the reason that we can do that is because molar mass, either of these forms, has grams and moles in it. And anytime you've got a unit with, or a number with 2 units in it, you can convert between those 2 units, as long as one's on the top, one's on the bottom. And we're going to do some more practice with that. We'll talk more about moles. So let's say that we want to calculate the mass of 2.46 times 10 to the 24 argon atoms. We are given a number of argon atoms. We are asked to find mass. We will need to recall from our memory what's argon. And hopefully we remember, or we can find it on our periodic table. Argon is Ar. And that is important because then we can go to our periodic table. We can find argon. It's one of our noble gases. It's between neon and krypton, all the way in the far right column. And we need that because we are going from argon atoms. I'm going to write that atoms argon. And what can we convert from atoms? What can we convert to from atoms? Moles. It's basically the only thing that we can convert to from atoms. Or we could convert to a different type of atoms if we had a chemical compound. So we can get to moles of argon. And where can we go from moles? We can use molar mass, and that will get us to grams of argon. Basically, right now, with where we are in the class, for moles, we can either change moles to atoms, we can change moles to grams. Those are kind of the 2 transformations that we can do with that unit. A big reason that we focus on units in chemistry is because we're going to be changing out the chemical pretty much all the time. It's almost always going to be a different chemical. But if we look at what units we have, we can learn the paths that we can take with those units. It's sort of a build your own adventure units addition. And right now, these are the 2 paths that we have for changing moles. If we have moles of argon, we could also change that to a different chemical, but we would need a balanced chemical reaction to do that. So this is what our solution map is going to look like. We're going to be using Avogadro's number to convert between atoms and moles. And then, like someone pointed out, we're going to be using molar mass to convert between moles and grams. Sometimes on exams, I will give you the molar mass. A lot of the time I won't. Don't expect me to give you the molar mass. So this is a calculation that we want to be getting good at. Get good at calculating molar mass. In this case, it's just the atom argon. And so we just find on our periodic table 39.95. Written under our argon, and that's the number we're going to use. Avogadro's number is the 6.022 times 10 to the 23. And that's going to be atoms in 1 mole. So starting with our very large number of argon atoms, we need to use our Avogadro's number to get from atoms to moles. The atoms part gets paired with Avogadro's number, so it's Avogadro's number of atoms. We have atoms, and so we have to put the atoms on the bottom in our conversion factor. So we're dividing by Avogadro's number. So the atoms will cancel. Our units that we have are moles and argon. If you wanted to, you could also include argon tagged on with atoms here as well as with moles. And that would make both atoms, argon, everything that we started with, it would make all units cancel. You can do that if you want to. It might make things a little bit nicer, easier to keep track of for you. I believe I did that last class. And then for our molar mass, the 39.95 grams per mole, we have moles and we want to go to grams, so we need the grams part to go on the top. So 39.95 grams, and this is another place where we can include the chemical label if we want to. I'll show that. And again, this will also make your units, it'll just keep them a little tidier. Throughout the problem, you won't have to go back and hunt for units like we've got argon hanging out back here. So those cancel. The argon and moles on the top cancel with the moles and the argon on the bottom. The units that we have left are grams of argon, and that is where we want to be. So we are going to be taking everything on the top and multiplying it and dividing by everything on the bottom. It's important, if you're going to use the times 10 raised to the power button or function on your calculator, you probably want to put parentheses around the 6.022 times 10 to the 23 that's on the bottom. Otherwise, there's a good chance you'll end up with some crazy exponent, something like 49 or 50 for your exponent, which shouldn't happen. So that could be a sign that you did something not quite all the way correct. If you're using that dolphin noise key, the EE, you do not have to use parentheses. For significant figures purposes, we'll round this to 163 grams argon. So if you have a calculator, try putting it in, make sure that you're getting the correct answer. We want to get our practice in, work out some of the bugs, work out some of the mistakes, make sure we know what we're doing with our calculator so that the only thing that we're really testing on the exam is our brain and how much we remember. We're not also testing our calculator skills and do we know how to put the numbers in correctly, because that can be very frustrating for us. All right, some more math stuff. Other ways that we can convert between different chemicals or talk about amounts of chemicals is with percent composition. Almost always this is just going to be mass percent composition, or we'll just call it mass percent. Oftentimes when you see some sort of an element or some sort of like an ingredient, the percentage, usually unless they specify otherwise, it's mass percent. We can calculate this for an element in a compound. So given any compound, how much of the mass of that compound, if we've got 100 grams of that compound, how much of that mass is going to be the element that we care about? And we have a formula for this one. I don't remember if I've given this on exam 2. If you look at the exam 2 practice materials module on Canvas, scroll basically all the way down to the bottom, the information sheet should already be posted. If this is on there, you don't have to have it memorized. If it's not on there, it would be a good idea to have it memorized. There will probably be at least one question using mass percent, possibly 2 or 3. And you will be using it on the homework, so you'll get some practice with it there. So the way that this works is we're taking the mass of X, where X is whatever element we care about, the mass of the element in a sample of the compound, divided by the mass of the entire compound. And then we're going to multiply that by 100%. So in this example problem that we've got this sample of chromium. It reacts with oxygen to form this many grams of the metal oxide. And a metal oxide is just metal and oxygen. We don't know what the ratio is because we don't know what species of chromium we have. We don't know if it's chromium 2, 3, 6, some other number. So we're just saying that it's an oxide, a metal oxide, to say that we've got metal and oxygen, and then that's it. So to find our mass percent of chromium, chromium is the thing we care about in this case. We're going to take the mass of our chromium, the 0.358 grams. We're going to use that on the top of our equation. We're going to use the 0.523 grams for the bottom of our equation, and we're going to multiply it by 100%. So let's set that up. So 0.358 grams CR on the top, 0.523 grams of the metal oxide. I'm just going to write metal oxide. Sometimes I write Crocs. Not like the shoe, but we don't know how many chromiums, how many oxygens we have, so sometimes we just put in a Y and an X there. I guess it might be cryox if we wanted to make it a word. So this is our metal oxide. The metal oxide, again, that's just our entire compound. It contains all of our chromium. And then as part of the equation, we multiply by 100%. The units are going to work out so that the grams cancel out, and the units that we're left over with are percent. So 0.35 divided by 0.523 times 100. This will be 68.5% chromium. Just by a raise of hands, how do we feel about this? Do we feel like we get it? Hands up. Do we feel like we don't get it? Hands down. Cool. Cool, cool, cool. We are going to continue using this. We're going to use it in some other ways as well. So we're going to invoke a little bit of algebra. You don't necessarily have to do the algebra. There's an alternate way to do it, which is just skipping the algebra part. All right, now let's say that we care about our macros. We care about the amount of fat, carbohydrates, and protein that we get in a day. We're counting our calories, but we also recognize that brownies are super delicious and we want to eat some brownies. So we know that the FDA recommends a person not consume more than 50 grams of added sugars in a day. If we're making 801 grams of brownies from scratch using 422 grams of sugar, what's the mass percent of sugar in the brownies? This is loosely based off of the Ghirardelli brownie mix that I had at home. So real world applications. I just guessed on the 801 grams. I didn't feel like making a batch of brownies just for an example problem, although that would have been a pretty good treat. What are we looking for in this problem? Mass percent of sugar. So we want to identify where's our question word. Question word is what? What is the mass percent of sugar? So we're looking for mass percent of sugar. We're going to be applying this equation. We're using the mass of part of the thing, that's the sugar, on top. The mass of the whole thing, that's the entire batch of brownies, on the bottom. And we're multiplying it by 100%. You should always get a number less than 100%. It wouldn't make sense for us to have more than 100% if that's just one of the components. If I've got two things and one of them is more than 100%, that's obviously not correct. Hopefully that's tracking. So the thing we care about, sugar and brownies. This is probably not a calculation that you would be doing at home, but it can be useful for another calculation that we're going to do next. So 422 grams sugar in our brownies. We have 801 grams of brownies, yummy, delicious brownies, times 100%. And we expect a number that's smaller than 100. If we're just comparing the numbers, 422 is about half. It's a little bigger than half of 800, so we'd expect it to be about 50%, maybe a little bigger. And the value that we get, 52.7%. What this tells us, quickly, visually, easily, hopefully, right, 52%, that's more than half. That means our brownies are more than half sugar. Not exactly a health food, right? Another thing that we can do with mass percent, other than just calculate it and use it to think about, oh, brownies are half sugar, another thing we can do with that is use it as a conversion factor. More likely, we're going to be using this. This is the wrong sig figs in this next example. It's fine. More likely, we're going to be using this for chemicals. But let's say that we want to use it to convert between different things. There's a couple ways that we can do this. One of the approaches is this 52.69%. Is 52.69 grams of whatever the thing is, sugar, and then 100 grams on the bottom of whatever it's in. In this case, that's going to be brownies. So this would be our conversion factor form, one of the conversion factor forms. So this would be our conversion factor between sugar and brownies. This is a more formulaic way of doing it, or more rote memorization way of doing it, rather, because the other way is using the actual formula. So you take the percentage, you put it on top, change it to grams, you put 100 grams on the bottom, make that the other thing. An alternative way of doing this would be to take the percent, turn it into a decimal, so slide the decimal place over 2 spots to the left, and that would be the amount of sugar per 1 gram of brownie. It's mathematically the exact same as what we've written up here. So that 52.69% goes in the top, 100 grams on the bottom. It's a conversion factor, so we could also flip the top and the bottom. So let's say that we want to figure out how much brownies can we eat. Let's say that we've cut out added sugar in the rest of our diet. We're just getting it through things like fruits and vegetables. We want to figure out what's the mass of brownie that we can have as a little treat to help supplement our strict caloric deficit that we're holding ourselves to, or our 300 gram excess, depending on what phase we're in. So what mass of brownie can you eat without exceeding the 50 grams suggested daily value for sugar? So we're looking for 50 grams of added sugar, and we've got the mass percent of the brownies. The number that we're going to start with here is the grams of sugar. So we're saying 50 grams of sugar is the maximum, and we're going to sugar to the max. So what's the maximum amount that we can have? Well, we can make a conversion factor with our 52.69%. How do we do that? Who remembers from the last slide? 52 on top, 100 grams on bottom. This is our starting point. So 52.69 grams sugar on the top, 100 grams brownie on the bottom. As written, what happens if we multiply this conversion factor with our 50 grams? Do the units work out nicely? Let me ooch it over there. I lost my hat. 5 lost its hat. They don't work out nicely, right? Because we've got we've got grams sugar on the top and also grams sugar on the top. So those are not going to cancel out. So this would be our sign. All right, well, we've got to flip it, and then the units will work out correctly. Let's move that back up there, and we'll write in the flipped version. So 100 grams brownie, the 52.69 grams sugar on the bottom. This makes our grams of sugar cancel. We'll get grams of brownie out. So this will tell us how much brownie can we eat. Do we expect the number to be more or less than 50, the number that we started with? If the brownies are about half sugar, we would need about double the amount of brownie to get the 50 grams of sugar. If that's just a thing that we can think through potentially to predict what our answer is going to be. So 50 times 100 divided by 52.69, the amount of brownie that we can eat. Look at that, it's right about double. 94.89 grams of brownie. And the sig figs are going to depend on how many we think that the daily value has. I don't think it's really that important in this particular scenario, but we could maybe say that it's 9 times 10 grams of brownie if we want to be really scientific, and we assume that the 50 grams is just one significant figure. If it's exact, then it would be the 94.89 grams of brownie. So that's one of the methods that we can do. Then we grab our little kitchen scale, we cut off a slice of brownie, we see is it around this 94, 95 grams mark. If it is, awesome, we eat it and we have a good time, and we go to bed feeling happy, hopefully. Any questions about the method that we used there? How we came up with the conversion factor, why we flipped it? Cool. Oh no. All right. I'm going to show us the other way real quick while we're here. The other way that we can do it, if you don't like this method, there's another one that works. It's the same thing. And the way that we do this is we use the mass percent formula. So mass percent equals percent of, sorry, not percent, grams of the part. In this case, that's sugar. Over grams of the whole thing. In this case, that's going to be the brownie, or brownies, times 100%. So in this equation, what is the term that we are looking for in this problem? Are we looking for mass percent, grams of the sugar, or grams of the brownie? We've got mass percent, we've got grams of sugar, so we're looking for grams of the brownies in this case. So since we're looking for grams of the whole thing, which is the brownies, we need to get that by itself, and then we've got our equation to solve. I'm going to plug numbers in first, because I think that's probably how a lot of us would do it. If you don't like plugging numbers in first, that's also a valid approach. So plugging in our mass percent, 52.69%. For mass percent, the grams of the part is the 50 grams of sugar. We've got the times 100%. That's just part of our formula. And then we have what we're looking for, which is the grams of brownies. How much brownie can we eat? This also helps us identify what we're looking for. It's the one thing that we don't have. It's the grams of the brownies. To solve for this, we need to move the grams of the brownies. It's currently on the bottom. We need to get it up to the top. We need to get it from the denominator where it is to the numerator where it will be. And then we need to get everything else on the other side, right? Classic algebra solve. The shortcut for this is we're going to swap the positions of the grams of brownie. That would be by multiplying it on both sides. That'll get it to cancel on the right. It'll move to the left. We're going to swap the sugar into that spot instead, dividing both sides by the percent sugar. So this will get us to grams of brownie equals 50 grams of sugar. And I'm going to take some minor liberties here and rewrite it in a slightly different way than we probably would expect it to be. So I'm putting the 52.69 under the 100 instead of under the grams of sugar. And if we compare the first solve, 50 times 100 over 52.69, with the formula version, we've got 50 times 100 divided by 52.69. It's the same exact solution. So we'll get the same answer. So you can use either of these two approaches, whichever one feels more comfortable for you, whichever one you think you like more. I'd say give them both a try when you're working on the homework for this section once we get there. Give them both a try. Maybe ask Logan for some extra help problems in the SI sessions, especially if you're having trouble with the algebra. He would love to go over the algebra with you in his SI sessions. We can also calculate mass percent composition or mass percent or percent composition from a chemical formula. This is easiest to do if we assume that we have 1 mole of the chemical. Let's look at mass percent composition of hydrogen in the chemical octane. So this is a problem that you could be given. Find the mass percent composition of hydrogen in octane. You would just be given the formula for octane. And you might think to yourself, this is crazy, Mr. K. You haven't given us any numbers. However, you have the elements, and we have a periodic table. We can go find our numbers. This is going to work the same way as before. Our mass percent formula, mass percent, equals grams of the things that we care about. In this case, that's hydrogen, since we're finding mass percent composition of hydrogen. And sneak a little hydrogen in on the left side here as well. And then on the bottom, we want the grams of octane, and then part of our formula times 100%. All right, Mr. K, still waiting for those numbers. So we need to look at, if we've got 1 mole of octane, we're using 1 mole because it makes the math easy. If we've got 1 mole of octane, how many grams of octane would that be? What do we need to do that problem? So here's the problem that we're finding. Right, we've got 1 mole of octane. We're just making that assumption, so the math is nice and easy. How do we get that to grams of octane? How do we do that conversion? We use molar mass. Anytime that we see moles and grams, and it's the same chemical, we want to train our brain to scream at us, molar mass. We don't have the molar mass. This is where the periodic table comes in. So our octane, we've got carbon, there are 8 of them. We have hydrogen, there's 18 of them, because we pulled these subscript numbers. The 8 behind the carbon means that we've got 8 carbons. The 18 behind the hydrogen means we've got 18 hydrogens. Then we pull from our memory or look at our yellow sheet or another periodic table, and we find the numbers for the molar masses for those. For carbon, it's going to be 12.011 grams per mole. For hydrogen, 1.008 grams per mole. Your numbers may be slightly different depending on your periodic table. So we're going to do 8 times 12 and change, plus 18 times 1 and change. You should get something that looks like 114.232 with units of grams per mole. Now what happens if we take 1 mole and multiply it by our molar mass? Very little, right? Almost nothing happens. All that this does really is our moles cancel, and now we've got our amount of octane in grams. This is why we're choosing 1 mole. It's because then our molar mass is the number that we would put into our mass percent equation. You could also just not remember the 1 mole part of it and just remember we put the molar mass in for the octane or for the chemical that we're using. So now we've got one of our 2 things solved. How many grams of hydrogen are we going to have? Think to yourself what that number is going to be or how we're going to find it. What's the closest whole number to the number that we're going to put in for grams of hydrogen? I'm thinking numbers like 1, 2, 3. Continue counting until you hit whatever number you're looking for. What's that number going to be? It's going to be about 18. Why is it going to be about 18 instead of just putting in 1?
Because there's 18 hydrogens.
We have 18 hydrogens in the octane, so we have to put in 18 hydrogens on the top. So this grams of hydrogen is 18 times 1.008 grams per mole, which will give us 18.144 grams per mole for our hydrogen. And that's the number that goes in 18.144 grams of hydrogen. It's because we've got 18 hydrogens in one of our octanes. That's where we would pull those 2 numbers from or summon them from. We take those numbers, put them in our calculator, times 100%, and it would be 15.883% hydrogen. Five significant figures from our, it should be 4 significant figures because of our 1.008 has 4 significant figures. We multiplied, we would take 4 significant figures through, and that's how we end up with 4 at the end. Let's do a practice problem with that. So I'll give you some time to work on this. Feel free to discuss with your neighbor. Please at least compare answers with your neighbor at the end if you're not chatting along the way. And the projector went off briefly because I zapped my computer. Fun. Okay, jumping into mass percent composition of oxygen. We want the mass percent composition of oxygen in acetic acid, and we were given that acetic acid is HC2H3O2. One place where we can run into trouble with some of these acids, particularly things like acetic acid is we've got a hydrogen in front, and we also have 3 hydrogens in the middle. So 1 in front, 3 in the middle, 4. We have 4 hydrogens. A common mistake with some of these is we forget about that 1 hydrogen that's out in front. So what we need to do with our formula is break it down into each of the individual elements that we have. We're calculating a molar mass. We have 4 hydrogens. We find their molar masses. We have 2 carbons. We look up their molar mass. And we've got 2 oxygens. Write down their molar mass. And then we're going to add all of that up. Should look something like 60.052 grams per mole. Where are we putting this number in our equation? We're putting it down below. 60.052 grams HC2H3O2. What are we going to put on the top? We want to put our oxygen, but not just 1 oxygen. We want to put the 2 oxygens. So 31.998 grams per mole. Sorry, grams. Oxygen, not hydrogen, not carbon, oxygen. 31.998 grams on the top times 100%. I think it will be 5 significant figures. So 31.998 divided by the thing on the bottom times 100. And we get 53.284% oxygen. So again, it's about half oxygen. Getting numbers close to 50% is pure coincidence. Questions about or confusions about any of the steps? Calculating molar mass, using the equation. It seems like we mostly had it, which is great. Moving on to empirical formulas. I believe that we've talked about empirical formulas. We can determine empirical formulas. If we haven't talked about empirical formulas, this would have been last chapter, I believe. An empirical formula is simplest whole number ratio of the elements. In a compound. So if we have subscripts, like in C8H18, 8 and 18 can both be divided by 2. This would turn into C4, H9. Do 4 and 9 have a common factor other than 1? They don't. We can't divide them. We could divide 4 by 4 or 2. We can't divide 9 by 4 or 2. So that would be our empirical formula. We can find these from mass percent composition. we would have to have multiple numbers for the mass percent composition. Oh, look at that. We haven't talked about it, and I put it on the next slide. That's very cool of me. So our empirical formula gives us the smallest whole number ratio. It's not the actual amount. The molecular formula is the actual number of each element. Actual number of atoms of each element. These would be good definitions for you to know. I don't know that they'll show up like as rote memorization points on the exam, but you will be asked questions about empirical formulas, molecular formulas. You want to know which one you're working with so that you know which one to find or which one to report. And an example for this would also be ethane, which is C2H6. We can divide both of those by 3, and that would turn into CH3. C2H6 would be our molecular formula. That's the actual number of carbons and hydrogens. And the empirical formula would be the simplified version, which is this CH3. We divided both of the subscripts by 2. So the 2 went away, the 6 turned into a 3. We can calculate this from experimental data. So this is apparently an experiment that you could do at home. You can separate water molecules into hydrogen gas and oxygen gas. I don't recommend doing this for a number of reasons. Playing with electricity around water is dangerous. Also, producing hydrogen gas and oxygen gas is dangerous. Those two are both flammable, and when you put them together in the same environment, it's extra flammable. They love to explode. So a little spark could end up with a big explosion. So you could do it at home, 9 to 12 volts. You could do it with a 9-volt battery, allegedly, and some double-sided pencils if you're a Sith. So a sample of water is decomposed. It's broken down into its constituent elements. It produces 4.5 grams of hydrogen, 36 grams of oxygen. How can we use these values to come up with an empirical formula? In an empirical formula, we're going to have some sort of hydrogen, some sort of oxygen. We don't know how many of each we're going to have, but they should be a countable amount. So we're going to need to convert our grams. What can we convert grams to? What can we convert grams to? Moles. We can convert it to moles using molar mass. And that's what we're going to do. And we've got the steps written out on the next slide. Block of text. So we're finding an empirical formula from experimental data. Let's just box in the whole slide in 2 colors so that you can come back and find it hopefully more easily. Let's not cover up the 28 though. So if we're finding an empirical formula from experimental data, the steps that we're going to use is we want to start with the masses of each element. Sometimes we'll be given a percent. There's a magic trick that we can do with a percent. If we have percentages, if we assume that we have 100 grams of the sample, percent turns into grams. You don't have to remember that we have 100 grams of the sample. You can just remember the magic trick. Percent turns into grams. Percent turns into grams. So if you're starting with percentages, don't get freaked out and like, oh, I don't have mass. Turn it into grams. Do your magic trick. So that's where we're going to start with the masses. In the example on the previous slide, right, we were given masses. So we're good to go. We don't have to do any magic tricks. So that's our first step, just what we have. And I like to write these out usually in separate rows, and then we're going to do a bunch of calculations all together, one at a time. We can then convert mass to moles. So we can go grams to moles using molar mass. And then we can divide all the moles by the smallest number of moles. And the reason that we're doing this is because the subscripts here, the X and the Y, whatever they are, these are going to be a ratio of hydrogens to oxygens or oxygens to hydrogens. And the way that we get a ratio or a relative amount is with division. Ratio basically just means divide. So we're going to divide by the smallest number of moles. Strictly speaking, you don't have to do this, but you would have to be absolutely cracked at math to be able to do this, or you'd have to be given really nice starting numbers, which is probably not going to happen. The reason we're dividing by the smallest number of moles is so that our smallest number is going to be 1. Our smallest ratio is going to be 1. All of our other numbers are going to be bigger than 1. Strictly speaking, you could do it with any of them, but do it by the smallest one. It just make your life easier that way. If the moles, if the ratio that we get after this, I'm going to write mole ratios. If the mole ratios are not whole numbers, things like 1, 2, 3, 4, countable numbers, we're going to multiply all of the moles to get numbers, and this is where this table comes in. You don't necessarily need this table, especially if you're cracked at math. Maybe not as cracked as earlier mentioned, but still, if you can take these endings, these fractional subscripts, and you can figure out what you need to multiply it by to get a whole number, awesome, you don't need the table. Otherwise, this might be a helpful table to come back and reference. So we're going to multiply all the moles to get whole numbers, and then we're going to write the formula using the mole ratios that we got here, maybe the ones we multiplied, if we multiplied, as subscripts for each element. That's a whole lot of words. Let's do some stuff with numbers. So the decomposition of water, that's the one that we saw a slide or two ago, produced hydrogen and oxygen. We want an empirical formula for water. Our first step is we want to start out with the grams of each. 4.5 grams of hydrogen, 36 grams of oxygen. First step done. Our second step, we want to convert to moles. So we're going to divide by our molar masses. I don't think I normally do it that way. Let's do it this way. That also looks weird, so I must have accidentally taken my crazy pills this morning. My apologies. They're the same color as the non-crazy pills, so that really throws things off. Okay, so our grams cancel. We're left with moles. So 4.5 divided by 1.008, 4.464, and more numbers. And instead of writing more numbers, what I'm going to do is write dot, dot, dot. I believe I've showed us this tech once before. What does the dot, dot, dot mean? It continues. And if you are going to use the dot, 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 to mean that there's more numbers, what this is also telling me is that you are going to use them. So if your calculator is not going to save these numbers for you so that you can go back and look at the extra numbers that you had, write all the numbers out. If your calculator, like mine, my beloved TI-36X Pro, if it has all the numbers and you go back and pull those numbers out, you can write the dot, 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 and then you can just pull that number out of memory. The calculator's memory, not yours. So that's the space-saving tech. And then we'll get 2.25 0 dot 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 moles oxygen. Do we have nice round neat numbers? We certainly do not. But that's great. That's okay. That's perfectly fine because we've got another step. So now on to step 3. Divide all the moles by the smallest number of moles. We've only got 2 here, so the smaller number of moles is, for oxygen, 2.25 and change. So we're going to divide both of these by that number. And what's nice about this is that one of these we get for free. Because we're dividing them both by the 2.25, we're dividing this number by itself. We get that one for free. We get to write in a 1. So this equals 1. No math, no serious math involved. My iPad thinks I have a lisp. And then the other one is going to be 1.984 dot dot dot. And the units that would be with these, for the top one, this is hydrogen to oxygen, or hydrogens per oxygen. Because we took hydrogen and we divided it by oxygen, this is our ratio of hydrogen to oxygen. The other one, this one's profound, this is the oxygens to oxygen, and wouldn't you know it, we've got 1 oxygen for every 1 oxygen. Wow, Mr. K, that's so cool. I just think that's silly, so that's why I pointed out. So no surprises there. So that's our third step. And now for our fourth step. If the mole ratios are not whole numbers, multiply all the moles to get whole numbers. There's a little bit of plus or minus. There's a little bit of wiggle room. If we're really close to a whole number, 1, 2, 3, 4, 5, etc., countable numbers, if we're really close to one of those, we're just going to round it. Do we think, hopefully we do we think 1.984 is close enough that we can just round it up to 2? Vigorous nodding ensues. Yes, we want to round that up to 2. So 2 hydrogens per oxygen, 1 oxygen for every oxygen. Now we can use these numbers as our subscripts. That's our step 5. So our elements, we had hydrogen. Our subscript in the hydrogen line, our subscript is 2. So H sub 2. Oxygen, in our oxygen line, our number was 1. So we just leave it blank. Water is H2O. For its empirical formula. It's also the molecular formula. How do we feel about those individual steps? It's a lot of steps. It's a memorizable pattern of steps. It's a practicable pattern of steps. This will show up on the exam. Dot, 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 indeed. A sample of a compound. Just any old compound is decomposed in the laboratory. It produces this many grams of iron, this many grams of oxygen. We want to calculate an empirical formula. We're starting with grams. We've got iron, We've also got grams of oxygen. We're going to make 2 lines. We're going to do all our calculations in those lines. If you don't want to do all your calculations in individual lines, that's okay. You can also do it a different way. This is the way that I like to do it. You can do it a different way if you really want to, if this doesn't work for you. So 34.97 grams of iron, 15.03 grams of oxygen. We will be doing these calculations for one of our labs. So there's also some practical aspect to it in that regard. So we've got our grams of iron, our grams of oxygen. We need to divide by our molar masses for each of these elements. So we'll sum in those out of our periodic table. Iron is 55.85 grams per mole. And this will give us the number of moles of iron and the moles of oxygen. Invoking once again that dot, dot, dot. So we get about 0.6 moles of iron, and we get about 0.9 moles of oxygen. Are these close enough that we can round? Wait a minute. We skipped a step. Don't forget to do the step where we divide by the smallest number of moles. That's another place where I see people make a mistake. For this type of problem, we forget about that step. It's a very important step. So we want to remember, divide by the smaller number or smallest number of moles. So that's the 0.62 and change moles of Fe. Sorry if I alarmed anyone with my wait a minute. I'm sure that's going to come through normally on the recording. All right, one of these we get for free. It's this top one. 1 iron for every iron. Profound truths we're learning. And then for our oxygen divided by our iron, we get to use our calculator. If you have the TI-36 and you plugged in both of these calculations earlier and you got the 0.626 and the 0.939 with all their things behind it, if you press the up arrow, select the number you want, press enter, it pulls the whole number out, and you save yourself a ton of button presses. This doesn't work on all calculators, but on the 36X Pro it does. Casio might have something that does it too, but I've never been a Casio user, so I wouldn't know. So 1.500 dot, 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 and this is oxygen over or per Fe. Are these numbers close enough that we can round? No, we are not close enough that we can round. But 1.500 is very close to 1.5. If we have a 0.5 at the end, how could we get rid of that? By multiplying.
By 2.
If we multiply by 2, if we needed to, we could refer back to our table. If it ends in 0.50, multiply everything by 2. That'll give us whole numbers. So times 2, times 2. So we've got 2 irons, and we've got 3 oxygens. These are now our subscripts for our elements. Fe2O3. We're writing the Fe, the iron, first because it's the metal. The more metallic element goes first. Fe2O3. Questions about our process there? Yes? So this divide by 0.626, this is our step 3. This is so that we get numbers that are closer to like a normal ratio. If you don't do this, then I have no clue what we would multiply these two things by. So this gives us nicer, neater numbers if we do this division. But we're choosing the smaller of the two. We're using the smaller one because that way we get 1 for this one. We get a number that's bigger for the other one. If we divided by the bigger one, we would get 1 for the oxygen, and we get 0.66, I think, for the iron. And that is a little bit more challenging. Usually works out nicer if you divide by the smaller number. When we get to the lab where we do these, we're doing this, our numbers are not going to be this nice and neat. We're going to have a little bit of extra wiggle room, plus or minus. On exams, in class examples, they'll typically work out to be really close to one of these fractional subscripts, or it's close enough that we can just round it to a whole number. We can also do empirical formula, 3 elements. We will pick up on this slide next week, Tuesday. If you want to, and I might even recommend this to you, give this a try. Try this problem before next class so that you've got something to compare to when we come back to it and start here next time.